Subscribe to Boring Science for sleep for new videos every day. Now, let us begin. The world's oceans, which collectively encompass approximately 361 million square kilometers of the Earth's surface, contain within their vast and slowly shifting volumes a quantity of dissolved mineral salts that has been the subject of sustained scientific inquiry for well over 2 centuries. The presence of these dissolved substances, referred to in aggregate as ocean salinity, is among the most fundamental physical properties of seawater, and it is a property that influences, in ways both direct and remarkably subtle, the density of the water column, the movement of deep ocean currents, the distribution of marine organisms, and the overall regulation of the planet's climate system. It is, in essence, a measurement of how much salt is dissolved in a given mass of water, and while this may appear to be a straightforward concept, the reality of measuring, mapping, and understanding ocean salinity across the entirety of the global ocean has proven to be an endeavor of considerable complexity and painstaking effort. The average salinity of the world's oceans is approximately 35 parts per thousand, which is to say that in every kilogram of typical seawater, there are roughly 35 grams of dissolved salts. This figure, 35 parts per thousand, sometimes expressed as 35 practical salinity units, has remained relatively stable over geological timescales, though it does exhibit meaningful variation from one region of the ocean to another, and from the surface to the deepest abyssal plains. The dissolved salts that contribute to this figure are not a single substance, but rather a mixture of several different ions, each present in a remarkably consistent proportion relative to the others, a principle that was first articulated in the 19th century and that has come to be known as the principle of constant proportions, or Marset's principle, named after the Swiss-born chemist Alexander Marset, who noted in 1819 that the ratios of the major dissolved ions in seawater appeared to be uniform regardless of the total concentration of salt. The most abundant dissolved ion in seawater is chloride, which accounts for approximately 55% of the total dissolved salts by mass. Chloride ions, each carrying a single negative electrical charge, are present in concentrations of roughly 19.4 grams per kilogram of standard seawater. The second most abundant ion is sodium, which constitutes approximately 30.6% of the dissolved material, present at a concentration of about 10.8 grams per kilogram. Together, sodium and chloride account for approximately 85.6% of all dissolved salts in seawater. And it is the combination of these two ions that is responsible for the characteristic salty taste that one notices upon inadvertently swallowing a mouthful of ocean water. The third most abundant constituent is sulfate, the doubly charged negative ion of sulfur and oxygen, which makes up approximately 7.7% of the dissolved salts, present at a concentration of about 2.7 grams per kilogram. Following sulfate in abundance is magnesium, a doubly charged positive ion that constitutes approximately 3.7% of the total dissolved material, amounting to roughly 1.3 grams per kilogram. Calcium, another doubly charged positive ion, accounts for approximately 1.2% of dissolved salts, present at about 0.41 grams per kilogram. Potassium, a singly charged positive ion, contributes approximately 1.1% at a concentration of roughly 0.39 grams per kilogram. Smaller, but still measurable quantities of bicarbonate, bromide, strontium, boron, and fluoride are also present, though each of these constitutes less than 1% of the total dissolved material. The remarkable constancy of these proportions across the world's oceans is a consequence of the extremely long residence times of the major ions in seawater relative to the mixing time of the ocean itself. The residence time of an ion is defined as the average length of time that an atom of that element remains dissolved in the ocean before being removed by some process, such as biological uptake, precipitation as a mineral on the seafloor, or incorporation into sedimentary deposits. Sodium, for example, has an estimated residence time of approximately 68 million years, while chloride has a residence time of approximately 100 million years. These enormously long periods mean that the inputs of these ions from rivers, hydrothermal vents, and other sources are effectively balanced by their removal, and because the ocean mixes on a time scale of roughly 1,000 to 2,000 years, the proportions of these ions have had ample time to become thoroughly homogenized throughout the entire global ocean. Minor ions with shorter residence times, such as iron or aluminum, do exhibit greater spatial variability, but the major ions that dominate the salinity measurement maintain their characteristic ratios with a consistency that is, from an analytical standpoint, quite striking. The measurement of ocean salinity has a history that extends back several centuries, though the early attempts were necessarily crude by modern standards. In the 17th century, Robert Boyle, the Anglo-Irish natural philosopher who is perhaps better known for his contributions to the understanding of gas behavior, conducted some of the earliest systematic investigations into the saltiness of seawater. Boyle attempted to measure the density of seawater samples and to relate this density to the amount of dissolved material, though his methods lacked the precision that would be achieved by later investigators. In the 18th century, Antoine Lavoisier, the French chemist whose work laid the foundations of modern chemistry, performed careful evaporation experiments on seawater samples, weighing the residue left behind after the water had been driven off by gentle heating. These evaporation-based methods, while conceptually simple, were plagued by difficulties arising from the fact that certain volatile compounds could be lost during the heating process, and certain hydrated minerals would retain varying amounts of water depending on the conditions of drying, leading to inconsistent results. The development of more precise methods of salinity determination accelerated in the 19th century, driven in part by the growing interest of naval powers in understanding the physical properties of the oceans through which their vessels traveled. One of the most significant contributions to the measurement of ocean salinity came from the work of the Danish chemist and oceanographer Martin Knudsen, who in the early 20th century developed a set of standard tables relating the chlorinity of seawater to its total salinity. Chlorinity, defined as the total mass of chlorine, bromine, and iodine contained in 1 kilogram of seawater, assuming that the bromine and iodine have been replaced by an equivalent mass of chlorine, was found to bear a highly consistent relationship to total salinity, expressed by the formula salinity equals 1.8065 times chlorinity plus 0.03. This relationship, established through meticulous titration experiments in which silver nitrate was used to precipitate the halide ions from known masses of seawater, provided a practical means of determining salinity with reasonable accuracy, and it remained the standard method for several decades. The technique of measuring salinity through electrical conductivity emerged as the preferred method during the second half of the 20th century. The principle underlying this approach is that dissolved ions in seawater carry electrical charge and therefore increase the ability of the water to conduct an electrical current. By measuring the electrical conductivity of a seawater sample at a known temperature and pressure, and comparing this measurement to the conductivity of a standard reference solution, it is possible to determine the salinity of the sample with a precision that greatly exceeds what could be achieved by chemical titration. The standard reference solution used for this purpose is known as International Association for the Physical Sciences of the Ocean Standard Seawater, which is prepared and distributed by a laboratory in the United Kingdom from carefully filtered and well-mixed samples of North Atlantic seawater. This standard seawater has a precisely known conductivity ratio, and all salinity measurements made by the conductivity method are ultimately traceable to this reference material. In 1978, the Joint Panel on Oceanographic Tables and Standards introduced the Practical Salinity Scale, commonly abbreviated as PSS 78, which defines salinity in terms of the conductivity ratio of a seawater sample to a standard potassium chloride solution at a temperature of 15 degrees Celsius and a pressure of 1 standard atmosphere. Under this scale, a seawater sample with a conductivity ratio of 1.0000 relative to the standard potassium chloride solution, which has a concentration of 32.4356 grams per kilogram, is assigned a practical salinity of 35. The practical salinity scale represented a significant advance in standardization, as it provided a universally agreed-upon definition that could be consistently applied by researchers working in different laboratories and on different research vessels around the world. The units of practical salinity are dimensionless, though they are sometimes informally referred to as practical salinity units, or PSU, a usage that purists in the field occasionally object to on the grounds that a dimensionless quantity should not, strictly speaking, be assigned units. Refractometry represents another method by which salinity can be determined, albeit one that is generally less precise than the conductivity method for scientific work. The refractive index of seawater, which describes how much the speed of light is reduced as it passes through the medium, is affected by the concentration of dissolved salts, as well as by temperature and pressure. By measuring the refractive index of a seawater sample with an optical refractometer, it is possible to estimate its salinity, and this technique finds practical application in field situations where a rapid approximate measurement is sufficient, such as in aquaculture operations or in educational settings. More recently, in the early 21st century, the thermodynamic equation of seawater 2010, known as TUS 10, was introduced as a replacement for the practical salinity scale, providing a more thermodynamically rigorous framework for describing the properties of seawater that takes into account the composition anomalies that can arise from the addition of river water or from biogeochemical processes in the deep ocean. Under TOS 10, the concept of absolute salinity, expressed in grams per kilogram, was introduced to complement the practical salinity, allowing for a more complete description of the thermodynamic state of seawater. Perhaps no single event in the history of oceanographic salinity measurement is as significant as the voyage of HMS Challenger, which departed from Portsmouth, England, on the 21st of December, 1872, and did not return until the 24th of May, 1876, having traveled approximately 68,890 nautical miles across the Atlantic, Pacific, Indian, and Southern Oceans. The Challenger expedition, organized under the scientific direction of Professor Charles Wyville Thomson of the University of Edinburgh and funded by the British Royal Society and the Royal Navy, was the first large-scale systematic attempt to study the physical and biological properties of the deep ocean. Over the course of the 3.5-year voyage, the scientific staff aboard the Challenger collected water samples from 362 stations distributed across the world's oceans, measuring the temperature, density, and chemical composition of seawater at various depths using the best instruments available at the time. The salinity measurements obtained during the Challenger expedition, while less precise than those achievable with modern conductivity instruments, provided the first comprehensive picture of how ocean salinity varies with geography and depth. The expedition's chemist, John Young Buchanan, performed careful analyses of the collected water samples, determining their specific gravity and chlorine content through laborious wet chemical methods that required considerable skill and patience to execute reliably on a moving vessel. The results, published in the 50-volume Challenger reports over the period from 1880 to 1895, revealed that surface salinity was highest in the subtropical regions and lower at the equator and in the high latitudes, a pattern that subsequent investigations would confirm and elaborate upon in much greater detail. The Challenger expedition also established the general principle that the deep ocean is relatively uniform in its salinity, with values typically falling in the narrow range of 34.6 to 35 parts per thousand, a finding that would prove important for understanding the circulation of the deep ocean in the decades that followed. The legacy of the Challenger expedition extended far beyond its specific measurements. The voyage demonstrated that the systematic study of the ocean's physical and chemical properties was both feasible and scientifically valuable, and it inspired subsequent generations of oceanographers to mount their own expeditions and to develop improved instruments and methods for studying the sea. The German meteor expedition of 1925 to 1927, the Swedish deep-sea expedition of 1947 to 1948, and the International Indian Ocean Expedition of 1959 to 1965 all built upon the foundation laid by the Challenger, progressively refining the global picture of ocean salinity and its relationship to ocean circulation patterns. In the decades following the Challenger expedition, the understanding of what determines the total amount of dissolved salt in the ocean evolved considerably. The primary sources of dissolved ions to the ocean are rivers, which carry weathering products from continental rocks to the sea, and hydrothermal vents on the mid-ocean ridges, where superheated water circulating through newly formed oceanic crust dissolves minerals and carries them into the ocean. Submarine volcanism and the dissolution of atmospheric gases at the sea surface also contribute, though to a lesser extent. The removal of dissolved ions from the ocean occurs through biological processes, such as the construction of calcium carbonate shells by marine organisms, through the precipitation of evaporite minerals in restricted basins, through adsorption onto sediment particles, and through the chemical reactions that occur at hydrothermal vents, where some ions are added to the ocean water while others are removed. The balance between these inputs and outputs, maintained over millions of years, determines the long-term average salinity of the ocean, which geochemical evidence suggests has fluctuated somewhat over geological time, but has remained within a range that is broadly similar to the present-day value for at least the past several 100 million years. The total mass of dissolved salt in the world's oceans is estimated to be approximately 4.8 times 10 to the 16th metric tons, or 48 million billion metric tons. If this salt were extracted from the ocean and spread evenly over the Earth's entire land surface, it would form a layer approximately 150 meters thick, a figure that serves to illustrate, in a rather mundane fashion, the truly enormous quantity of dissolved material that the oceans contain. The volume of the world's oceans is approximately 1.335 billion cubic kilometers, and at an average salinity of 35 parts per thousand and an average density of approximately 1,025 kilograms per cubic meter. The mass of seawater in the global ocean amounts to roughly 1.37 times 10 to the 21st kilograms, of which approximately 4.8 times 10 to the 19th kilograms consists of dissolved salts. These numbers are, it must be acknowledged, approximations, but they serve to convey the scale of the phenomenon under discussion. The measurement of salinity in the modern era has been greatly facilitated by the development of electronic instruments capable of making rapid and precise measurements in situ, that is, at the actual location in the water column where the measurement is desired, rather than requiring that a water sample be brought to the surface and analyzed in a shipboard laboratory. The most widely used instrument for this purpose is the conductivity temperature depth profiler, commonly referred to by its abbreviation CTD, which is lowered through the water column on a cable from a research vessel and records continuous profiles of electrical conductivity, temperature, and pressure as it descends. From these three measurements, salinity can be calculated at every point in the profile using the equations of the practical salinity scale, or, more recently, the TOS 10 framework. A typical CTD casts to the full depth of the ocean, which may be 4,000 to 6,000 meters in areas away from the continental shelves, takes approximately 2 to 3 hours to complete, including the time required to lower the instrument, allow it to stabilize at depth, and retrieve it to the surface. During this time, the instrument records thousands of individual measurements, producing a detailed vertical profile of salinity, temperature, and density that can be analyzed to identify the different water masses present in the water column and to trace their origins and pathways through the ocean. The precision of modern CTD instruments is remarkable. Current generation instruments are capable of measuring conductivity with a precision of approximately plus or minus 0.0003 Siemens per meter, temperature with a precision of plus or minus 0.001 degrees Celsius, and pressure with a precision of plus or minus 0.015% of the full-scale range. These measurement precisions correspond to a salinity precision of approximately plus or minus 0.002 practical salinity units, which is sufficient to resolve the subtle differences in salinity that characterize the different deep water masses of the ocean. The calibration of these instruments against standard seawater samples, typically performed before and after each research cruise, ensures that measurements made by different instruments on different vessels can be meaningfully compared, a requirement that is essential for building a coherent global picture of ocean salinity from the combined efforts of many individual research programs. The accumulation of salinity measurements over the past century and a half has resulted in the construction of comprehensive climatological atlases of ocean salinity, such as the World Ocean Atlas maintained by the National Oceanic and Atmospheric Administration of the United States, which compiles and quality controls salinity observations from research vessels, autonomous profiling floats, and other platforms into grid fields that represent the average state of the ocean on monthly, seasonal, and annual timescales. These atlases, which are periodically updated as new observations become available, provide the baseline against which changes in ocean salinity over time can be detected and assessed, and they serve as essential reference datasets for the initialization and validation of numerical ocean circulation models. The most recent edition of the World Ocean Atlas, published in 2023, incorporates observations from the Argo program, a global array of nearly 4,000 autonomous profiling floats that drift freely in the ocean, descending to a depth of 2,000 meters every 10 days and recording profiles of temperature and salinity as they rise to the surface, where they transmit their data via satellite before descending again to repeat the cycle. The Argo program, which was initiated in the year 2000 and represents one of the most ambitious sustained ocean observation programs ever undertaken, has transformed the field of physical oceanography by providing, for the first time, a quasi-global, year-round sampling of the upper 2,000 meters of the ocean. Prior to Argo, the vast majority of subsurface ocean observations were collected by research vessels, which, despite their capabilities, could only sample a tiny fraction of the ocean at any given time, and whose operations were concentrated along major shipping routes and in regions of particular scientific interest, leaving large areas of the ocean, particularly in the southern hemisphere and in the remote reaches of the South Pacific and South Indian Oceans, essentially unobserved. The Argo floats, each of which costs approximately $20,000 and has a typical operational lifetime of approximately 4 to 5 years before its batteries are exhausted, have filled many of these observational gaps, and the data they have collected have revealed patterns of temperature and salinity variability that were previously unknown or only dimly suspected. Each Argo float follows a repeating cycle that begins with the float sinking to its parking depth, typically 1,000 meters, where it drifts with the currents for approximately 9 days. At the end of this drift period, the float descends further to its profiling depth, typically 2,000 meters, and then ascends to the surface, measuring temperature, salinity, and pressure continuously as it rises. Upon reaching the surface, the float transmits its accumulated data to the Iridium or Argo satellite systems, receives any updated mission instructions, and then sinks again to begin the next cycle. The entire profiling cycle, from surface to 2,000 meters and back, typically takes approximately 6 hours, during which the float records measurements at intervals of approximately 2 meters in depth, producing a profile that contains roughly 1,000 individual data points. The data are subjected to rigorous quality control procedures, both automated and manual, before being made freely available to the global research community through the Argo data centers, typically within 24 hours of collection. The Deep Argo program, an extension of the original Argo concept to the full depth of the ocean, has been under development since approximately 2012 and is gradually deploying floats capable of profiling to depths of 4,000 to 6,000 meters. These deep floats are designed to sample the abyssal layers of the ocean that are below the reach of standard Argo floats and that are known to play important roles in the thermohaline circulation and in the storage of heat and carbon in the deep ocean. The technical challenges of operating autonomous instruments at the enormous pressures found at these depths, which can exceed 600 atmospheres, are considerable, and the development of pressure-resistant housings, reliable buoyancy engines, and accurate sensors capable of functioning under these extreme conditions has required significant engineering effort. As of 2025, approximately 200 deep Argo floats have been deployed, primarily in the Southern Ocean, the North Atlantic, and the South Pacific. And the data they've collected are already providing new insights into the variability and trends in deep ocean temperature and salinity that were previously inaccessible to routine observation. The geographic distribution of salinity across the surface of the world's oceans is governed by the interplay of several physical processes, each of which acts to either add fresh water to or remove fresh water from the ocean surface, thereby diluting or concentrating the dissolved salts in the upper layer of the water column. The most important of these processes are evaporation, which removes fresh water from the ocean surface and leaves the dissolved salts behind, thereby increasing salinity; precipitation, which adds fresh water to the ocean surface and dilutes the dissolved salts, thereby decreasing salinity; river discharge, which introduces large volumes of fresh water from continental drainage basins into coastal and marginal seas; and the formation and melting of sea ice, which selectively rejects salt during freezing and releases fresh water during melting. The relative magnitudes of these processes vary systematically with latitude, longitude, and season, producing a complex but broadly predictable pattern of surface salinity that has been mapped in progressively greater detail over the past century and a half. The highest surface salinities in the open ocean are found in the subtropical regions, centered at approximately 20 to 30 degrees latitude in both hemispheres. In these regions, the descending branch of the atmospheric Hadley circulation produces persistently dry conditions with high rates of evaporation and low rates of precipitation, resulting in a net removal of fresh water from the ocean surface and a corresponding increase in salinity. Surface salinities in the subtropical North Atlantic, for example, commonly exceed 37 practical salinity units, and in the central region of the North Atlantic subtropical gyre, values as high as 37.5 have been recorded. The subtropical South Atlantic exhibits a similar pattern, though the maximum salinities are slightly lower, typically around 36 to 36.5 practical salinity units, reflecting the somewhat greater precipitation in the southern hemisphere subtropics compared to the northern hemisphere. The subtropical regions of the Pacific Ocean also exhibit elevated surface salinities, though the absolute values are generally lower than those in the Atlantic, with maxima typically in the range of 35 to 36 practical salinity units, owing to the greater width of the Pacific Basin and the correspondingly greater influence of precipitation from tropical weather systems. At the equator, surface salinity is generally lower than in the subtropics, as the intertropical convergence zone, a band of atmospheric convergence and ascending air that circles the globe near the equator, produces abundant rainfall that dilutes the surface waters. In the eastern tropical Pacific, where the intertropical convergence zone is particularly well developed and persistent, surface salinities can drop below 34 practical salinity units, and in some coastal areas influenced by major river outflows, such as the region off the mouth of the Amazon River, surface salinities can fall below 33 or even 32 practical salinity units over large areas. The Amazon River, which has an average discharge of approximately 209,000 cubic meters per second, making it the largest river in the world by volume, introduces such an enormous quantity of fresh water into the tropical Atlantic that its influence on surface salinity can be detected hundreds of kilometers from its mouth, extending northwestward along the coast of South America and into the Caribbean Sea. In the high latitudes, Surface salinity is also relatively low compared to the subtropics, though for somewhat different reasons. In the subpolar and polar regions, precipitation exceeds evaporation on an annual basis, and the melting of sea ice during the spring and summer months releases fresh water that had been locked up in the ice during the preceding winter. In the Arctic Ocean, surface salinities are particularly low, commonly falling in the range of 28 to 33 practical salinity units, reflecting the combined influence of river discharge from the Great Siberian and North American rivers, such as the Ob, Yenisei, Lena, and Mackenzie, and the seasonal cycle of sea ice formation and melting. The total freshwater input to the Arctic Ocean from rivers is estimated at approximately 4,200 cubic kilometers per year, a figure that, when distributed over the relatively small area of the Arctic Basin, produces a significant dilution of the surface waters. The Southern Ocean, which encircles the Antarctic continent, also exhibits relatively low surface salinities, typically in the range of 33.5 to 34.5 practical salinity units. As a consequence of the excess of precipitation over evaporation and the freshwater released by the melting of Antarctic icebergs and the seasonal retreat of the sea ice edge. The freshwater budget of the Southern Ocean is further complicated by the presence of the Antarctic ice sheet itself, which calves icebergs at a rate of approximately 2,000 cubic kilometers of ice per year. Each cubic kilometer of ice representing approximately 917 million cubic meters of freshwater that, upon melting, contributes to the dilution of the surrounding seawater. The effects of evaporation and precipitation on ocean salinity are not merely local phenomena. They are linked to the global water cycle, the continuous movement of water between the ocean, atmosphere, land, and ice sheets that is driven by solar energy and that represents one of the most fundamental biogeochemical cycles operating on the surface of the Earth. Each year, approximately 430,000 cubic kilometers of water evaporate from the ocean surface, of which approximately 390,000 cubic kilometers return directly to the ocean as precipitation, while the remaining approximately 40,000 cubic kilometers fall as precipitation over land and eventually returns to the ocean by a river discharge and groundwater flow. This imbalance between oceanic evaporation and oceanic precipitation means that the ocean is, on a net basis, a source of atmospheric moisture. And the transport of this moisture from the ocean to the continents and back is intimately connected to the patterns of salinity that are observed at the ocean surface. River discharge represents a concentrated source of fresh water that can produce dramatic local reductions in salinity, particularly in semi-enclosed seas and coastal regions. The Baltic Sea, a semi-enclosed body of water in northern Europe that is connected to the North Atlantic through the narrow and shallow Danish Straits, provides a particularly striking example of the effects of river discharge on salinity. The Baltic Sea receives freshwater input from numerous rivers draining the surrounding lands of Scandinavia, Finland, the Baltic states, Poland, Germany, and Russia. with a total annual discharge of approximately 440 cubic kilometers. At the same time, the restricted connection to the open ocean limits the inflow of saline Atlantic water, resulting in a pronounced salinity gradient from the Danish Straits, where salinities may reach 20 to 25 practical salinity units, to the innermost reaches of the Gulf of Bothnia and the Gulf of Finland, where surface salinities may fall as low as 2 to 5 practical salinity units. This gradient, which extends over a distance of approximately 1,500 kilometers, makes the Baltic Sea one of the largest bodies of brackish water on Earth. And the organisms that inhabit it must be adapted to salinities that are intermediate between those of fresh water and those of the open ocean, a condition that limits the biodiversity of the Baltic compared to fully marine or fully freshwater environments. At the opposite extreme, certain semi-enclosed seas that are situated in arid regions and that have restricted connections to the open ocean exhibit salinities that substantially exceed the oceanic average. The Mediterranean Sea, which is connected to the Atlantic Ocean through the Strait of Gibraltar, a narrow passage approximately 14 kilometers wide and with a sill depth of approximately 284 meters, receives relatively little freshwater from rivers and precipitation compared to the amount of water that is lost through evaporation in its warm and sunny climate. The result is that the average salinity of the Mediterranean is approximately 38 to 39 practical salinity units, substantially higher than the Atlantic average of approximately 35.5. The excess evaporation over the Mediterranean creates a deficit that is balanced by the inflow of Atlantic surface water through the Strait of Gibraltar, which is compensated at depth by an outflow of dense, saline Mediterranean water that spills over the sill of the strait and descends into the Atlantic, where it can be traced as a distinct water mass, known as Mediterranean outflow water. At depths of approximately 800 to 1,200 meters across much of the eastern North Atlantic. The Red Sea, which is even more isolated from the open ocean and situated in an even more arid environment than the Mediterranean, exhibits salinities that are among the highest found in any major body of seawater, commonly reaching 40 practical salinity units and in some restricted areas exceeding 41. The Red Sea is connected to the Indian Ocean through the Bab el-Mandeb Strait, a passage approximately 30 kilometers wide with a sill depth of approximately 137 meters, and it receives almost no freshwater input from rivers. As the surrounding lands of the Arabian Peninsula and the northeastern African coast are among the driest regions on Earth. The evaporation rate over the Red Sea is estimated at approximately 200 centimeters per year, while precipitation amounts to only approximately 5 to 10 centimeters per year, creating an enormous freshwater deficit that drives a vigorous exchange flow through the Bab el-Mandeb, with relatively fresh Indian Ocean water flowing in at the surface and dense, saline Red Sea water flowing out at depth. The Persian Gulf, also known as the Arabian Gulf, presents another example of a semi-enclosed sea with elevated salinity, though its characteristics are somewhat different from those of the Mediterranean and the Red Sea. The Persian Gulf has an average depth of only approximately 35 meters and is connected to the Indian Ocean through the Strait of Hormuz, which has a sill depth of approximately 100 meters. Evaporation rates are high, and the freshwater input from the Shat al-Arab river system, formed by the confluence of the Tigris and Euphrates rivers, is concentrated in the northwestern end of the Gulf. The result is a salinity gradient that increases from approximately 37 practical salinity units in the northwest to approximately 40 or more in the shallow waters of the southeastern end, where extensive coastal salt flats, known as sabkhas, provide evidence of the extreme evaporative conditions. The relationship between salinity and the density of seawater is of fundamental importance to physical oceanography, as it is the variations in density, produced by variations in both temperature and salinity, that drive the thermohaline circulation of the deep ocean. The density of seawater is a function of three variables: temperature, salinity, and pressure. At a given pressure, increasing the salinity of seawater increases its density, while increasing its temperature decreases its density, at least for temperatures above the temperature of maximum density, which for seawater with a salinity of 35 practical salinity units is approximately minus 3.8 degrees Celsius, well below the freezing point of seawater at that salinity. The relative influence of temperature and salinity on density varies, depending on the temperature of the water. At high temperatures, a given change in temperature produces a larger change in density than the same change in temperature would produce at low temperatures, because the thermal expansion coefficient of seawater increases with temperature. Conversely, the effect of salinity on density is relatively constant across the range of temperatures found in the ocean. The density of surface seawater in the open ocean typically ranges from approximately 1,021 kilograms per cubic meter in warm, relatively fresh tropical waters to approximately 1,028 kilograms per cubic meter in cold, saline high-latitude waters. These differences may appear small in absolute terms, amounting to a variation of only about 7 kilograms per cubic meter out of a total density of more than 1,000 kilograms per cubic meter. But they are sufficient to drive the large-scale circulation patterns of the deep ocean, as even very small density differences, when acting over the vast horizontal distances of the ocean basins, can generate significant pressure gradients that set the water in motion. Because the density differences involved are so small relative to the total density, physical oceanographers commonly work with a quantity known as sigma T, defined as the density of seawater at a given temperature and salinity and at atmospheric pressure, minus 1,000 kilograms per cubic meter, which allows the relatively small but oceanographically important density variations to be expressed as numbers in the range of approximately 21 to 28, rather than as numbers in the range of 1,021 to 1,028. The concept of potential density is a further refinement that accounts for the compressibility of seawater under the enormous pressures found in the deep ocean. When a parcel of seawater is moved from the surface to a depth of 4,000 meters, the pressure increases by approximately 400 atmospheres, and this compression increases the density of the water by approximately 2%, even though neither its temperature nor its salinity has changed. To remove this pressure effect and allow meaningful comparisons of density between water parcels at different depths, oceanographers calculate the potential density, which is the density that a water parcel would have if it were brought adiabatically. That is, without exchanging heat with its surroundings, to a reference pressure, typically the pressure at the sea surface. This concept is essential for determining the stability of the water column, that is, whether a water parcel at a given depth is lighter than, heavier than, or of the same density as the water above and below it. A determination that has profound implications for vertical mixing and for the formation of distinct layers, or strata, within the water column. In the deep ocean, below the thermocline, which is the layer of rapid temperature decrease that separates the warm surface waters from the cold deep waters, and that is typically found at depths of 200 to 1,000 meters, depending on latitude and season. The salinity of seawater falls within a remarkably narrow range. The deep waters of the Atlantic Ocean, for example, have salinities that typically lie between 34.8 and 35.1 practical salinity units, while the deep waters of the Pacific Ocean are slightly fresher, with salinities typically in the range of 34.6 to 34.7 practical salinity units. These subtle differences in deep water salinity reflect the different sources and ages of the deep water masses in each basin, a topic that will be explored in considerably greater detail in subsequent sections of this discussion. The North Atlantic deep water, which is formed in the high-latitude North Atlantic and which fills much of the deep Atlantic basin, has a salinity of approximately 34.9 to 35 practical salinity units, while the Antarctic bottom water, which is formed near the Antarctic continent and which spreads northward along the bottom of the ocean basins, has a slightly lower salinity of approximately 34.6 to 34.7 practical salinity units, reflecting the incorporation of relatively fresh glacial meltwater during its formation. The vertical structure of salinity in the ocean is characterized by a feature known as the halocline, which is a layer of the water column in which salinity changes rapidly with depth. In many regions of the ocean, particularly in the subtropics, the halocline coincides approximately with the thermocline, as the warm, salty surface waters overlie the cooler, less saline deep waters. In the high latitudes, however, the situation can be reversed, with relatively fresh surface waters overlying salter deep waters, creating a halocline that acts to stabilize the water column and inhibit vertical mixing. In the Arctic Ocean, the strong halocline created by the input of fresh water from rivers and ice melt plays a crucial role in insulating the sea ice from the warmer, salter Atlantic water that lies at intermediate depths. And any weakening of this halocline, as might occur in response to changes in river discharge or ice melt patterns associated with climate change, could potentially expose the sea ice to increased heat flux from below, accelerating its thinning and retreat. This interaction between salinity stratification and sea ice represents one of the many feedback mechanisms that make the climate system of the polar regions both complex and sensitive to perturbation. The seasonal variation of surface salinity is most pronounced in regions where the seasonal cycles of precipitation, evaporation, and river discharge are strongest. In the tropics, the seasonal migration of the intertropical convergence zone produces alternating wet and dry seasons in many coastal regions, leading to corresponding oscillations in surface salinity. In the Bay of Bengal, for example, the annual monsoon cycle produces dramatic seasonal changes in salinity, with surface values dropping to as low as 28 to 30 practical salinity units during the summer monsoon season. When the combined discharge of the Ganges, Brahmaputra, and other rivers reaches its annual maximum, and rising to 33 to 34 practical salinity units during the drier winter months. The amplitude of these seasonal salinity variations in the Bay of Bengal is among the largest found anywhere in the world's oceans, and the resulting density stratification has important implications for the intensity of tropical cyclones that form in this region, as the fresh surface layer can act as a barrier to the entrainment of cooler subsurface water that would otherwise limit the intensity of the storm. In the mid-latitudes, seasonal variations in surface salinity are generally smaller than those in the tropics, as the seasonal cycles of precipitation and evaporation are less extreme. However, in coastal regions influenced by the spring snowmelt discharge of major rivers, significant seasonal freshening of the surface waters can occur. The discharge of the Mississippi River into the Gulf of Mexico, for example, peaks in the spring months of March through May, when snowmelt from the vast drainage basin of the Mississippi and its tributaries, which covers approximately 3.2 million square kilometers, or about 40% of the contiguous United States, delivers large volumes of freshwater to the northern Gulf. This freshwater input produces a plume of reduced salinity that can extend hundreds of kilometers from the river mouth, and its seasonal variation has important implications for the ecology of the Gulf of Mexico, as the nutrients carried by the river discharge fuel the growth of phytoplankton that can, in excessive quantities, lead to the formation of hypoxic zones, commonly known as dead zones, in the bottom waters of the continental shelf. The Dead Sea, situated at the border between Israel, Jordan, and the Palestinian territories, while technically a lake rather than a sea, provides an instructive extreme case of what happens when evaporation vastly exceeds all sources of freshwater input in an enclosed basin. The salinity of the Dead Sea is approximately 340 grams per liter, which is roughly 9.7 times the average salinity of the open ocean, making it one of the most hypersaline water bodies on Earth. The extreme salinity of the Dead Sea is a consequence of its location in the Jordan Rift Valley, at an elevation of approximately 430 meters below sea level, in one of the most arid regions of the world, where evaporation rates are high and precipitation is minimal. The only significant source of fresh water is the Jordan River, whose flow has been greatly reduced over the past several decades by water diversions for agricultural and domestic use in Israel, Jordan, and Syria, leading to a steady decline in the level of the Dead Sea, which has fallen by approximately 1 meter per year over recent decades, with the surface area shrinking correspondingly. The extreme salinity of the Dead Sea prevents all but the most specialized microorganisms from surviving in its waters, and the buoyancy of objects in the dense brine is noticeably greater than in ordinary seawater, a property that has made the Dead Sea a popular tourist attraction. The interannual variability of ocean salinity, that is, the variation from one year to the next that cannot be accounted for by the regular seasonal cycle, is increasingly recognized as an important indicator of changes in the global water cycle. Observations from the Argo float array and from satellite-based salinity measurements have revealed that over the past several decades, there has been a general tendency for the salter regions of the ocean to become salter and for the fresher regions to become fresher, a pattern that is consistent with an intensification of the global water cycle in response to rising atmospheric temperatures. This pattern, sometimes described colloquially as the rich getting richer and the poor getting poorer, reflects the fact that a warmer atmosphere can hold more moisture, leading to enhanced evaporation in the already dry subtropical regions and enhanced precipitation in the already wet tropical and high-latitude regions. The magnitude of the observed salinity changes, while small in absolute terms, is statistically significant when assessed over the multi-decadal period for which reliable observations are available, and it provides independent evidence, complementary to direct measurements of precipitation and evaporation, that the global water cycle is indeed intensifying in response to anthropogenic climate change. The thermohaline circulation of the world's oceans is a vast, slow, and profoundly important system of deep ocean currents that is driven by differences in the density of seawater, which are themselves produced by differences in temperature and salinity, the two properties from which the term thermohaline derives its name. This circulation system, which connects the surface and deep waters of all the major ocean basins in a continuous, interconnected flow, plays a central role in the redistribution of heat from the tropics to the high latitudes, in the ventilation of the deep ocean with dissolved oxygen, in the transport of nutrients and carbon dioxide between the surface and the abyss, and in the regulation of the Earth's climate on timescales ranging from decades to millennia. The thermohaline circulation is, in a very real sense, the circulatory system of the ocean and its behavior, its variability, and its potential responses to climate change are among the most actively studied topics in modern oceanography and climate science. The fundamental mechanism that drives the thermohaline circulation is the formation of dense water at the ocean surface in certain high-latitude regions, where cooling and, in some cases, the increase in salinity associated with the formation of sea ice combine to produce water that is sufficiently dense to sink from the surface to great depths. This process, known as deep water formation, occurs in only a few specific locations around the world, and it is these locations that serve as the starting points, or source regions, for the deep limb of the thermohaline circulation. Once formed, the dense deep water spreads slowly through the ocean basins, filling them from the bottom up, and eventually returns to the surface in other regions through a combination of upwelling processes, where it is warmed and freshened before being transported back to the regions of deep water formation to complete the circuit. The entire cycle, from the sinking of a parcel of water in the high latitudes to its eventual return to the surface and subsequent transport back to the sinking region, is estimated to take approximately 1,000 years. Though this figure is necessarily an approximation, as the transit time varies considerably depending on the specific pathway followed by the water parcel through the complex three-dimensional circulation of the global ocean. The most well-studied and arguably the most climatically significant component of the thermohaline circulation is the Atlantic Meridional Overturning Circulation, commonly abbreviated as AMOC, which encompasses the northward flow of warm, saline surface water in the upper layers of the Atlantic Ocean, the formation of deep water in the high-latitude North Atlantic, the southward flow of this deep water through the Atlantic Basin, and the eventual return of the water to the surface through upwelling in the Southern Ocean and elsewhere. The AMC is responsible for the transport of approximately 1.3 petawatts of heat northward across the equator and the Atlantic, which is equivalent to approximately 1.3 times 10 to the 15th watts, a quantity that is roughly comparable to the total electricity generation capacity of the entire world. This northward heat transport is the reason why the climate of northwestern Europe is considerably warmer than the climate of other regions at the same latitude. London, at approximately 51.5 degrees north, has an average January temperature of approximately 5 degrees Celsius, while Labrador, at the same latitude on the opposite side of the Atlantic, has an average January temperature of approximately minus 20 degrees Celsius. The formation of North Atlantic deep water, the dense water mass that constitutes the deep southward flowing limb of the AMOC, occurs primarily in two regions: the Labrador Sea, situated between the eastern coast of Canada and the western coast of Greenland, and the Nordic Seas, which include the Greenland Sea, the Iceland Sea, and the Norwegian Sea, situated between Iceland, Greenland, and Northern Europe. In both regions, the process of deep water formation is initiated by the intense cooling of surface waters during the winter months, when cold, dry air masses from the continental interiors sweep out over the relatively warm ocean surface, extracting heat and moisture at prodigious rates. In the Labrador Sea, the surface cooling during particularly severe winters can produce convective mixing that extends to depths of 2,000 meters or more, homogenizing the water column and producing a characteristic water mass known as Labrador seawater, which has a temperature of approximately 3 to 4 degrees Celsius and a salinity of approximately 34.8 to 34.9 practical salinity units. The production of Labrador seawater is highly variable from year to year, depending on the severity of the winter cooling, and in some mild winters, deep convection may not occur at all. In the Nordic seas, the process of deep water formation is somewhat different, involving not only surface cooling, but also the increase in salinity that occurs when sea ice forms in the marginal ice zone. When seawater freezes, the growing ice crystals preferentially exclude dissolved salts, a process known as brine rejection, which produces a concentrated brine that is denser than the surrounding water and that sinks, carrying with it the elevated salinity that contributed to its excess density. The combination of surface cooling and brine rejection in the Nordic seas produces several distinct deep water masses, including Greenland sea deep water and Norwegian sea deep water, which have temperatures in the range of -1 to 1 degree Celsius and salinities of approximately 34.9 practical salinity units. These deep water masses overflow the submarine ridges that separate the Nordic seas from the Atlantic proper, primarily through the Denmark Strait between Iceland and Greenland, where the sill depth is approximately 620 meters, and through the Faroe Bank Channel between the Faroe Islands and Scotland, where the sill depth is approximately 840 meters. As this overflow water descends the southern slopes of the ridges, it entrains surrounding ambient water, approximately doubling in volume and acquiring the characteristics of the mature North Atlantic deep water that fills the deep Atlantic basin. The southward flow of North Atlantic deep water through the Atlantic basin has been traced using a variety of observational techniques, including the measurement of temperature, salinity, dissolved oxygen, and various chemical tracers such as chlorofluorocarbons, which are synthetic compounds that entered the ocean through gas exchange at the surface, and that can be used to date the age of a water mass, that is, the time elapsed since it was last in contact with the atmosphere. The North Atlantic deep water flows southward as a deep western boundary current along the continental margin of the Americas, at depths typically between 1,500 and 4,000 meters, with a volume transport of approximately 15 to 20 spheredrups, where one spheredrup is defined as a volume flow rate of 1 million cubic meters per second, or approximately 100 times the combined discharge of all the world's rivers. This deep boundary current can be traced southward along the coast of North America, past the equator, and along the coast of South America to the southern tip of the continent, where it enters the Southern Ocean and begins to spread eastward under the influence of the powerful Antarctic circumpolar current. The other major source of deep water in the global thermohaline circulation is the Antarctic bottom water, which is formed in several locations around the margin of the Antarctic continent, most notably in the Weddell Sea, in the Ross Sea, and along the coast of Adélie Land. The formation of Antarctic bottom water involves a process similar to that which produces deep water in the Nordic seas, with intense surface cooling and brine rejection during winter sea ice formation combining to produce extremely cold, dense water that sinks to the very bottom of the ocean. Antarctic bottom water is the densest water mass in the world ocean, with temperatures typically in the range of -0.8 to 2 degrees Celsius and salinities of approximately 34.6 to 34.7 practical salinity units. Despite its lower salinity compared to North Atlantic deep water, its extremely low temperature makes it denser, and it occupies the very deepest layers of the ocean basins, filling the abyssal plains of the Atlantic, Pacific, and Indian Oceans from the bottom up. The volume of Antarctic bottom water produced each year is estimated at approximately 8 to 10 spheredrups in the Weddell Sea alone, with additional contributions from the Ross Sea and other formation sites, bringing the total to perhaps 15 to 20 spheredrups, a figure that is comparable to the production rate of North Atlantic deep water. The spreading of Antarctic bottom water northward from its source regions has been traced using temperature and salinity measurements, as well as chemical tracers, and it has been found to penetrate well into the northern hemisphere in both the Atlantic and Pacific basins, reaching as far north as approximately 40 degrees north in the Atlantic and approximately 12 degrees north in the Pacific. The transit time for Antarctic bottom water to travel from its formation sites to the remote reaches of the North Pacific, which represents the end point of the deep ocean circulation, is estimated at approximately 800 to 1,000 years, a figure that has been corroborated by radiocarbon dating of deep water samples. The concept of the global thermohaline circulation as a single interconnected system, linking the deep water formation regions of the North Atlantic and the Southern Ocean with the rest of the world's oceans in a continuous loop, was popularized by the American geochemist Wallace Smith Broecker, who in 1987 introduced the term Great Ocean Conveyor Belt to describe this circulation in a widely read article published in the journal Natural History. Broecker's conveyor belt metaphor, while necessarily a simplification of the complex, three-dimensional, and highly variable real ocean circulation, captured the essential features of the thermohaline circulation in a way that was accessible to a broad audience, and that proved enormously influential in shaping both scientific and public understanding of the ocean's role in the climate system. In Broecker's formulation, warm, salty surface water flows northward in the Atlantic, cools and sinks in the high-latitude North Atlantic, flows southward at depth through the Atlantic, joins the Antarctic circumpolar current, and spreads into the deep Pacific and Indian Oceans, where it gradually warms and rises to the surface, eventually returning to the Atlantic to close the loop. This simplified picture, while omitting many important details, such as the role of wind-driven upwelling in the Southern Ocean and the complex recirculation patterns in the deep ocean basins, nonetheless provided a useful conceptual framework for understanding the large-scale features of the thermohaline circulation and its potential sensitivity to perturbation. The estimated transit time of approximately 1,000 years for a complete circuit of the global thermohaline circulation means that this system has a very long memory, in the sense that changes in the properties of the deep water form today will continue to influence the temperature, salinity, and chemical composition of the deep ocean for centuries to come. This long time scale also means that the thermohaline circulation responds slowly to external forcing, whether natural or anthropogenic, and that the full consequences of any perturbation to the system may not be apparent for many generations. The thermohaline circulation is, in effect, a repository of climatic information spanning the past millennium, and the properties of the deep water masses that fill the ocean basins carry within them a record of the conditions that prevailed at the ocean surface at the time and place of their formation. The climate implications of the thermohaline circulation are profound and far-reaching. By transporting enormous quantities of heat from the tropics to the high latitudes, the AMOC moderates the climate of the North Atlantic region, warming northwestern Europe by an estimated 5 to 10 degrees Celsius relative to what would be expected based on latitude alone. The thermohaline circulation also plays a critical role in the carbon cycle, as the formation of deep water carries dissolved carbon dioxide from the surface ocean, where it has been absorbed from the atmosphere, to the deep ocean, where it is effectively sequestered from the atmosphere for hundreds to thousands of years. This process, known as the solubility pump, is responsible for the transfer of approximately 2 to 3 gigatons of carbon per year from the atmosphere to the deep ocean, representing a significant fraction of the total oceanic uptake of anthropogenic carbon dioxide. The possibility that the AMC might weaken or even collapse in response to anthropogenic climate change has been a subject of intense scientific scrutiny and considerable public concern since the early 1990s. The basic mechanism by which climate change could disrupt the AMC is straightforward. As the climate warms, increased precipitation and river discharge in the high-latitude North Atlantic, combined with the accelerated melting of the Greenland ice sheet, would increase the freshwater input to the regions where deep water formation occurs. This additional freshwater would reduce the salinity and hence the density of the surface waters in these regions, potentially inhibiting or preventing the deep convection that drives the formation of North Atlantic deep water and, by extension, the entire AMC. Climate model simulations generally project that the AMC will weaken over the course of the 21st century, with most models predicting a decline of approximately 25 to 30% by the year 2100 under high-emission scenarios, though the range of projections is wide. And some models predict a much more dramatic weakening, while others project only a modest decline. Paleoclimate evidence strongly supports the idea that the AMOC has undergone dramatic changes in the past, including abrupt shutdowns and recoveries associated with the glacial cycles of the Pleistocene epoch. During the last glacial period, which ended approximately 11,700 years ago, a series of rapid climate oscillations known as Danskard-Oshger events produced temperature swings of up to 10 to 15 degrees Celsius over Greenland within the span of a few decades. And these events have been attributed to abrupt changes in the strength of the AMC triggered by pulses of freshwater from the melting of the Laurentide ice sheet, which covered much of North America during the glacial period. The most dramatic of these events was the Younger Dryas, a period of abrupt cooling that began approximately 12,900 years ago and lasted for approximately 1,200 years, during which temperatures in the North Atlantic region dropped to near glacial levels before recovering equally abruptly. The Younger Dryas has been attributed to a massive release of freshwater from glacial Lake Agassiz, a vast lake that had formed behind the retreating Laurentide ice sheet in central North America into the North Atlantic via the St. Lawrence River system, producing a sudden reduction in the salinity of the surface waters in the deep water formation regions and shutting down the AMO Sea. The observational record of AMO Sea strength in the modern era is relatively short, with continuous direct measurements dating back only to 2004, when the Rapid MoCA monitoring array was established across the Atlantic at 26.5 degrees north. This array, which consists of an array of moored instruments that continuously measure the temperature, salinity, and velocity of the water column from the surface to the seafloor, has revealed that the AMO Sea has an average strength of approximately 17 spheredrops, but with substantial variability on timescales ranging from days to years. In the spring of 2009 to 2010, the Rapid Array detected a temporary but dramatic reduction in AMO Sea strength, with the overturning circulation dropping to approximately 12 spheredrops for a period of several months, coincident with an anomalously cold winter in Europe and eastern North America. Whether this event represented a transient fluctuation or the beginning of a longer-term decline is a question that continues to be debated, though subsequent measurements have shown a partial recovery. Longer-term indicators of AMO Sea strength, based on proxy records such as sediment grain size, the distribution of temperature-sensitive microfossils, and geochemical tracers in marine sediment cores, suggest that the AMO Sea may have been weakening since the mid-20th century, and that its current strength may be at or near its lowest level in at least 1,000 years. A study published in 2018, based on the analysis of sea surface temperature patterns in the North Atlantic, concluded that the AMO Sea had weakened by approximately 15% since the mid-20th century. A finding that is broadly consistent with the predictions of climate models, though the attribution of this weakening to anthropogenic climate change, as opposed to natural variability, remains a subject of ongoing research. The potential consequences of a significant weakening or collapse of the AMO Sea would include a reduction in the northward heat transport in the Atlantic, leading to cooling of the North Atlantic region and northwestern Europe, changes in precipitation patterns across the northern hemisphere, a southward shift of the intertropical convergence zone, affecting rainfall in the Sahel region of Africa and in South America, acceleration of sea level rise along the eastern coast of North America, and a reduction in the oceanic uptake of carbon dioxide, which would accelerate the buildup of carbon dioxide in the atmosphere and amplify global warming. The deep ocean circulation is not limited to the thermohaline processes described above. It is also influenced by wind-driven processes, particularly in the Southern Ocean, where the powerful westerly winds that circle the Antarctic continent drive a northward transport of surface water through Ekman dynamics. the deflection of wind-driven surface currents by the Coriolis effect. This northward Ekman transport draws deep water upward to replace the surface water that has been moved away, a process known as wind-driven upwelling that is believed to play a central role in closing the thermohaline circulation by returning deep water to the surface in the Southern Ocean. The interaction between wind-driven and thermohaline processes in determining the strength and structure of the global overturning circulation is complex and not yet fully understood, and it represents one of the frontier areas of research in physical oceanography and climate science. Numerical models of the ocean circulation, which solve the equations of fluid motion on a three-dimensional grid representing the ocean basins, are essential tools for exploring these interactions. Though the models are necessarily imperfect representations of the real ocean and must be carefully validated against observational data, the mixing of deep water masses as they travel through the ocean basins is another process that plays an important role in the thermohaline circulation as it gradually modifies the temperature, salinity, and chemical properties of the deep water along its pathway. Mixing in the deep ocean occurs through both turbulent processes generated by the breaking of internal waves on rough bottom topography, and through the slow lateral diffusion that occurs along surfaces of constant density. The energy required to mix the deep ocean against the stabilizing effect of the density stratification is ultimately derived from the tides and the winds, and the global rate of deep ocean mixing is a subject of considerable uncertainty, with estimates ranging from approximately 2 terawatts to 10 terawatts, or 2 times 10 to the 12 watts to 10 times 10 to the 12 watts. This mixing is not uniformly distributed throughout the ocean, but is concentrated in regions of rough bottom topography, such as mid-ocean ridges, fracture zones, and submarine seamounts, where the interaction of tidal currents with the irregular seafloor generates turbulence that is orders of magnitude stronger than that found over the smooth abyssal plains. The thermohaline circulation also interacts with the atmosphere through its influence on sea surface temperatures, which in turn affect atmospheric circulation patterns, precipitation, and storm tracks. The anomalously warm sea surface temperatures in the North Atlantic that result from the northward heat transport by the AC create a region of enhanced evaporation and atmospheric instability that influences the development and track of weather systems across the North Atlantic and northwestern Europe. Changes in the strength of the AC, whether natural or anthropogenic in origin, can therefore produce changes in weather patterns that are felt far from the ocean, in a striking demonstration of the interconnectedness of the Earth's climate system. The study of these ocean-atmosphere interactions and of the role of the thermohaline circulation in mediating them is a central concern of climate science, as it is through these interactions that the slow, deep ocean component of the thermohaline circulation can exert an influence on climate variability on timescales that are relevant to human societies. The influence of ocean salinity on marine life is pervasive and inescapable, as every organism that inhabits the sea must contend with the osmotic challenges presented by the dissolved salts in its environment. Osmoregulation, the process by which organisms maintain the concentration of dissolved substances in their body fluids within a tolerable range despite differences between the internal and external environments, represents one of the fundamental physiological challenges faced by marine organisms, and the strategies that different groups of organisms have evolved to meet this challenge are remarkably diverse. Marine invertebrates, such as jellyfish, sea anemones, and most species of marine worms, are generally osmoconformers, meaning that the osmotic concentration of their body fluids closely matches that of the surrounding seawater, and their cells have evolved to function optimally at the ionic concentrations characteristic of the ocean. When the salinity of the surrounding water changes, as may occur in estuaries or in coastal regions influenced by river discharge, the body fluids of these organisms change in concert, and if the salinity change is too great or too rapid, cellular function may be impaired or the organism may die. Marine fish, in contrast, are osmoregulators, actively maintaining the concentration of dissolved substances in their blood and body fluids at levels that are substantially different from those of the surrounding seawater. Marine bony fish, or teleosts, maintain their blood osmolarity at approximately 300 to 400 milliosmoles per liter, which is roughly one-third the osmolarity of seawater at a salinity of 35 practical salinity units. Because their body fluids are more dilute than the surrounding seawater, marine teleosts face the constant challenge of water loss by osmosis and salt gain by diffusion across their gills and other permeable surfaces. To compensate, they drink seawater continuously, absorbing the water through their intestinal lining and excreting the excess salt through specialized cells in their gills known as chloride cells, or ionocytes, which actively pump sodium and chloride ions out of the body against the concentration gradient, a process that requires a continuous expenditure of metabolic energy. A typical marine teleost may drink an amount of seawater equivalent to 10 to 20% of its body weight each day, and the energetic cost of osmoregulation has been estimated at approximately 5 to 10% of the fish's total metabolic budget. Marine cartilaginous fish, such as sharks and rays, have adopted a fundamentally different strategy for dealing with the osmotic challenge of life in the sea. Rather than maintaining body fluids that are substantially more dilute than seawater, these animals retain high concentrations of urea and trimethylamine oxide in their blood, raising the osmotic concentration of their body fluids to a level that is approximately equal to, or slightly higher than, that of the surrounding seawater. This strategy, known as ureosmotic regulation, eliminates the osmotic gradient across the body surface and therefore eliminates the problem of water loss, though it requires that the animal's enzymes and cellular machinery be adapted to function in the presence of high concentrations of urea, which in most other vertebrates would be toxic or disruptive to protein function. The trimethylamine oxide that is co-retained with urea is believed to serve as a counteracting osmolyte, stabilizing protein structure against the denaturing effects of urea. At the extremes of the salinity spectrum, certain organisms have evolved to thrive in conditions that would be lethal to most marine life. Halophilic microorganisms, or halophiles, are organisms that require elevated salt concentrations for optimal growth, and they are found in hypersaline environments such as salt lakes, solar evaporation ponds, and the brine pools that form in certain deep-sea basins where concentrated salt deposits dissolve into the overlying water. Extreme halophiles, such as certain species of the archaeal genus Halobacterium, can grow in salt concentrations approaching saturation, approximately 300 grams per liter, which is roughly 8.5 times the salinity of normal seawater. These organisms have evolved a variety of biochemical adaptations to cope with the extreme osmotic stress, including the accumulation of compatible solutes such as potassium chloride or organic compounds such as betaine and ectoine, and the modification of their proteins to remain functional at high ionic strength. The practical extraction of salt from seawater, or the production of fresh water from seawater through desalination, represents a domain in which the chemistry of ocean salinity intersects with human technology and economics. Salt production from seawater by solar evaporation is one of the oldest industrial activities in human history, with evidence of organized salt production dating back to at least 3,000 years before the Common Era in coastal regions of China, India, and the Mediterranean. The basic principle is simple. Seawater is admitted to shallow ponds, where it is exposed to sunlight and wind, and as the water evaporates, the dissolved salts become progressively more concentrated until they begin to crystallize out of solution. Sodium chloride, being the most abundant dissolved salt and having a relatively simple crystallization behavior, is the primary product, though the residual brine, known as bitterns, contains elevated concentrations of magnesium, potassium, and other valuable ions that can be extracted through further processing. Global production of sea salt by solar evaporation is estimated at approximately 50 to 60 million metric tons per year, with the largest producers being China, India, Australia, and the countries bordering the Mediterranean. Desalination, the removal of dissolved salts from seawater or brackish water to produce fresh water suitable for human consumption, irrigation, or industrial use, has become an increasingly important technology in arid and semi-arid regions of the world where freshwater resources are scarce. The global desalination capacity was approximately 107 million cubic meters per day as of 2022, with the largest concentrations of desalination plants found in the Middle East, North Africa, and the Mediterranean region. The two principal technologies employed for large-scale desalination are reverse osmosis and thermal distillation, each of which exploits a different physical principle to achieve the separation of water from dissolved salts. Reverse osmosis desalination works by forcing seawater under high pressure through a semi-permeable membrane that allows water molecules to pass through while rejecting the dissolved salt ions. The pressure required to overcome the natural osmotic pressure of seawater and drive water through the membrane is typically in the range of 55 to 82 atmospheres, or approximately 800 to 1,200 pounds per square inch, depending on the salinity of the feedwater and the recovery rate of the system. Modern reverse osmosis membranes, typically constructed from thin-film composite polyamide materials, can achieve salt rejection rates of approximately 99.5 to 99.8%, producing permeate water with a salinity of less than 500 parts per million, which is well within the World Health Organization's guideline value for drinking water quality. The energy consumption of modern reverse osmosis desalination plants, which has decreased substantially over the past several decades thanks to improvements in membrane technology, energy recovery devices, and system design, is approximately 3 to 4 kilowatt-hours per cubic meter of fresh water produced, which is approaching the theoretical minimum energy requirement of approximately 1.06 kilowatt-hours per cubic meter dictated by thermodynamics. Thermal distillation, the other major desalination technology, works by heating seawater to produce steam, which is then condensed to yield fresh water, leaving the dissolved salts behind in the concentrated brine. The most widely used thermal desalination process is multi-stage flash distillation, in which the heated seawater is passed through a series of chambers or stages, each maintained at a successively lower pressure so that the water boils or flashes. At each stage, producing steam that is condensed on heat exchanger tubes to yield fresh water. A typical multi-stage flash plant may have 20 to 40 stages and can produce fresh water with a purity that exceeds that of reverse osmosis permeate, though at a higher energy cost, typically in the range of 8 to 12 kilowatt-hours per cubic meter. Multi-effect distillation, another thermal process, uses a series of evaporators in which the steam produced in one effect serves as the heating medium for the next, achieving better energy efficiency than multi-stage flash distillation. With energy consumption in the range of 6 to 8 kilowatt-hours per cubic meter. Thermal desalination plants are particularly common in the Persian Gulf region, where the availability of low-cost thermal energy from oil and gas production offsets the higher energy consumption of these processes relative to reverse osmosis. The concentrated brine that is produced as a byproduct of desalination, typically having a salinity approximately twice that of the feed water for reverse osmosis plants, represents an environmental challenge that must be managed carefully. The discharge of large volumes of hot, hypersaline brine into coastal waters can have adverse effects on marine ecosystems, particularly in enclosed or semi-enclosed basins where the flushing rate is low. The elevated salinity of the brine can cause osmotic stress in marine organisms, while the elevated temperature, the residual chemicals used in the pre-treatment of the feedwater, and the reduced dissolved oxygen concentration of the brine can all contribute to ecological damage in the vicinity of the discharge point. Various strategies have been developed to mitigate these impacts, including the dilution of the brine with cooling water or treated wastewater before discharge, the use of diffuser systems to promote rapid mixing and dilution in the receiving water, and the recovery of valuable minerals from the brine before disposal. The reconstruction of past ocean salinity, known as paleosalinity, from the geochemical and isotopic analysis of marine sediment cores represents one of the most challenging and fascinating areas of paleoceanography. Because salinity itself is not directly preserved in the geological record, paleoceanographers must rely on proxy indicators that are related to salinity through known physical or chemical relationships. One of the most widely used paleosalinity proxies is the oxygen isotope composition of the calcium carbonate shells of foraminifera, single-celled organisms that secrete shells of calcite or aragonite and that are abundantly preserved in marine sediments. The ratio of the heavy oxygen isotope, oxygen 18, to the lighter and more abundant oxygen 16 in foraminiferal shells is determined by both the temperature at which the shell was formed and the oxygen isotope composition of the seawater in which the organism lived. The oxygen isotope composition of seawater is, in turn, related to salinity, because the evaporation of water preferentially removes the lighter isotope, leaving the remaining water enriched in oxygen 18, while precipitation and river discharge add water that is depleted in oxygen 18. In regions where salinity variations are dominated by the balance between evaporation and precipitation, a positive correlation between salinity and oxygen 18 has been documented, allowing the oxygen isotope composition of fossil foraminifera to be used in combination with independent estimates of temperature to reconstruct past changes in salinity. Another approach to paleosalinity reconstruction involves the measurement of the magnesium to calcium ratio in foraminiferal shells, which is primarily a function of the temperature at which the shell was formed and can therefore be used to estimate past temperatures, which in turn allows the oxygen isotope signal to be separated into its temperature and salinity components. The barium to calcium ratio in planktonic foraminifera has also been proposed as a proxy for surface salinity, particularly in regions influenced by river discharge, as barium concentrations in seawater are elevated in areas of high freshwater input. However, each of these proxies is subject to various sources of uncertainty and potential bias, and the reconstruction of paleosalinity with quantitative precision remains a formidable challenge that requires the careful integration of multiple lines of evidence and a thorough understanding of the limitations of each proxy. The study of ocean salinity from space, using satellite-based instruments, represents one of the most significant technological advances in oceanography in the early 21st century. The European Space Agency's Soil Moisture and Ocean Salinity Mission, known by its acronym SMOS, was launched on the 2nd of November, 2009, and became the first satellite to provide global measurements of sea surface salinity from orbit. SMS carries a microwave radiometer that operates at a frequency of 1.4 GHz, corresponding to a wavelength of approximately 21 centimeters in the L-band of the electromagnetic spectrum. At this frequency, the thermal emission from the ocean surface is sensitive to the dielectric properties of seawater, which are in turn affected by the salinity of the water. As dissolved ions increase the conductivity of seawater and thereby modify its emissivity. By measuring the brightness temperature of the ocean surface at multiple angles and polarizations, and by applying a retrieval algorithm that accounts for the effects of sea surface temperature, surface roughness, atmospheric interference, and other confounding factors. SMS is able to estimate sea surface salinity with an accuracy of approximately 0.2 to 0.3 practical salinity units when averaged over periods of approximately 10 to 30 days and spatial scales of approximately 100 to 200 kilometers. The National Aeronautics and Space Administration of the United States launched its own dedicated ocean salinity mission, Aquarius, on the 10th of June, 2011, aboard the Argentine SCD spacecraft. Aquarius carried 3 microwave radiometers operating at the same L-band frequency as SMS, together with a scatterometer that provided independent measurements of surface roughness to improve the accuracy of the salinity retrieval. The Aquarius mission operated successfully until the 7th of June, 2015, when a power supply anomaly rendered the instrument inoperable, but during its nearly 4 years of operation, it provided valuable data on the global distribution and seasonal variability of sea surface salinity, with an accuracy of approximately 0.2 practical salinity units when averaged over monthly and 1-degree spatial scales. The data from Aquarius revealed, among other things, the detailed structure of the salinity field in the tropical Atlantic, including the seasonal migration of the Amazon River plume and the intertropical convergence zone, and the interannual variability of salinity in the tropical Pacific associated with the El Niño Southern Oscillation. The Soil Moisture Active Passive Mission, known as SMP, launched by NASA on the 31st of January, 2015, was designed primarily for soil moisture measurement. But its L-band radiometer also provides measurements of sea surface salinity as a secondary objective. The SMP radiometer has a spatial resolution of approximately 40 kilometers, significantly higher than that of SMS, and has achieved salinity measurement accuracies comparable to those of Aquarius. The data from SMP have been used to extend the satellite salinity record that began with SMS and Aquarius, providing a continuous time series of global sea surface salinity observations that is now more than 15 years long and that is proving invaluable for monitoring changes in the global water cycle and for improving the representation of ocean salinity in numerical ocean and climate models. The satellite observations of sea surface salinity, when combined with the in situ measurements from the Argo float array and from research vessels, provide an increasingly comprehensive picture of how ocean salinity is distributed across the globe and how it is changing over time. These observations have confirmed and quantified the intensification of the global water cycle that was hypothesized on the basis of theoretical considerations and climate model projections, showing that the salinity contrast between the evaporation-dominated subtropical regions and the precipitation-dominated tropical and high-latitude regions has increased by approximately 4 to 8% over the period from 1950 to the present. This finding has important implications for the future behavior of the thermohaline circulation, as the freshening of the high-latitude surface waters that is both observed and projected could, if it continues and intensifies, weaken the deep water formation processes that drive the Ames Sea, with consequences for regional and global climate that have been described in the preceding sections of this discussion. The history of salt in human civilization is, in itself, a subject of considerable extent, though only a brief mention is warranted in the present context. The word salary derives from the Latin salarium, which is believed to be connected to the allowance given to Roman soldiers for the purchase of salt. And the significance of salt as a commodity has been such that it has influenced the location of settlements, the routes of trade, and the outbreak of conflicts throughout recorded history. The salt trade routes of the Sahara, along which camel caravans transported blocks of salt from the mines of Tagaza and Tadeni to the markets of Timbuktu and beyond, were among the most important commercial arteries of medieval West Africa, and the value of salt in these transactions was, by some accounts, approximately equal to that of gold on a weight-for-weight basis. The production of salt from seawater by solar evaporation, as practiced in the coastal salt pans of the Mediterranean, India, and China, has been a continuous human activity for millennia, and the industrial-scale production of salt, both from seawater and from underground salt deposits, now amounts to approximately 300 million metric tons per year worldwide, of which only a small fraction is used for culinary purposes, the remainder being consumed by the chemical industry for the production of chlorine, sodium hydroxide, and other industrial chemicals. The measurement and understanding of ocean salinity, from the early attempts of Robert Boyle in the 17th century to the satellite missions of the 21st, represents a remarkable narrative of scientific progress, in which each generation of investigators has built upon the work of its predecessors to construct an increasingly detailed and nuanced picture of this fundamental property of the ocean. The dissolved salts that give seawater its characteristic taste and density are not merely a chemical curiosity. They are intimately connected to the circulation of the deep ocean, the regulation of the global climate, the distribution and physiology of marine life, and the availability of freshwater resources for human civilization. The ongoing monitoring of ocean salinity, through the combined efforts of satellite missions, autonomous floats, research vessels, and shore-based laboratories, will continue to be essential for understanding and predicting the behavior of the Earth's climate system in the decades and centuries to come, as the consequences of anthropogenic emissions of greenhouse gases continue to unfold, and as the slow but inexorable adjustment of the thermohaline circulation to the changing conditions at the ocean surface gradually makes itself felt in ways that may be subtle, but that will, over time, prove to be of profound significance. The steady accumulation of data points, each representing a single measurement of the electrical conductivity of a small volume of seawater at a specific location and depth, has, over the course of more than a century, produced a body of knowledge that is at once vast and incomplete, precise in its individual measurements and uncertain in its global syntheses, revealing in its broad patterns and tantalizingly ambiguous in its finer details. The ocean, which covers approximately 70.8% of the Earth's surface, and which contains approximately 97% of the planet's water, remains in many respects imperfectly known, and the salinity of its waters. Despite being one of the most frequently measured of all oceanographic variables, continues to present puzzles and surprises to those who study it. The gradual warming of the climate, the slow reshaping of the patterns of evaporation and precipitation that determine the distribution of salt in the surface ocean, the uncertain future of the great overturning circulations that connect the surface and the deep, and the responses of marine ecosystems to the changing chemical environment in which they find themselves are all threads in a complex and still unfolding narrative that will occupy the attention of oceanographers, climate scientists, and marine biologists for generations to come. It is worth noting in this connection that the very monotony of the subject matter, the repetitive cataloging of ions and their concentrations, the dry enumeration of measurement techniques and their associated uncertainties, the plodding accumulation of data from one research cruise to the next, is itself a reflection of the way in which scientific understanding of the natural world is actually built. It is not built from dramatic discoveries and revolutionary insights, though these do occur from time to time, but rather from the patient, methodical, and often tedious work of making careful measurements, recording them accurately, and comparing them with the measurements made by others in different places and at different times. The study of ocean salinity exemplifies this mode of scientific inquiry, and if the recounting of its details has had a soporific effect upon the listener, this is perhaps not entirely inappropriate, given that the ocean itself is, in its vast and unhurried rhythms, the very embodiment of patience and persistence, qualities that are also, it may be noted, conducive to the onset of restful sleep.